Thank you very much, and thanks for inviting me. I was asked to give a bit more general introduction because it's a broad audience. So I will, before I go into this main topic, I will talk briefly, give you my 50 cents about why I think what we are doing and what quantum science and quantum technology is doing is interesting. And if you go very far back, we have these two frameworks to describe our world for small and well-isolated systems and for large systems. And in the end, the question is, and that's also very heavily pursued in many different experiments in Vienna and elsewhere, the question is how much can we push this boundary between, okay, this screen doesn't show my pointer. All right, fine. How far can we push this boundary that is typically kicking in due to decoherence? And that you can view in different ways. What is macroscopicity? But the number of degrees of freedom is one, but maybe also the physical extent, which is something I will talk about. Maybe how can we make these machines bigger? And that's the question. Like, even if you're not interested in building a quantum and in selling a quantum computer, it's a valuable question to ask: how big can we make these systems and control them in a quantum way? Second question is, can we also make it useful for information processing, for example? And in either case, what we need to do to basically push this boundary ahead is to avoid errors as we control these systems. And I also want to give you an argument why it's important to avoid errors and not ignore it, like it was done for a long time in this what's called the NISQ area, where you focus on scaling. And interestingly, a Microsoft researcher who is also, Microsoft is doing a lot to promote hype in this area, but there's also one who helps us ground ourselves. And I want to cite here Matthias Treuer, who said, we can do about 1 billion more operations per unit time on a classical chip that we have today, compared to a future quantum computer we plan to build that we don't have yet today. It's what we plan to do. And that is a huge constant factor which we have to beat by any scaling law. And his conclusion is that big data problems are just not going to happen because the I/O properties are too slow, and that quadratic speedups are not going to cut it to overcome it. And this is taken from a not so recent arXiv article anymore. Just as an example, some 100-spin 2D Ising model calculating its quantum dynamics, factoring a 2048 integer, and a quantum chemistry example. Maybe you've seen this before. This is for to calculate the ground state of a catalyst for nitrogen fixation, for example. What you see here is that one thing you see, this is for different qubit types. Either you have nanosecond gates or microsecond gates, and either you have some 10 to the minus 3 infidelity or 10 to the minus 4 or projected Majorana infidelities of 10 to the minus 6. What you can see is that if you do quantum dynamics and you have slow gates, okay, instead of a second, you wait an hour. But if you want to do this quantum chemistry simulation, the same factor relates to, okay, we have to wait a month, but oh, I'm not going to live long enough to see the result. So one conclusion is we need fast clock speeds. That is one conclusion I think I take from this. The other conclusion is, do you really need to have this rather simple example to get a full solution with the commonly known and currently known error correction protocols? You need about 10 million qubits, physical qubits, to encode this problem with 100 spins. So having 1/9 more in the infidelity allows it to do this with 1/10 of the resources. And once maybe funding is not as abundant anymore, a factor of 10 in cost matters, and also a factor of 10 in complexity. So I would say this is, of course, has to be taken with a grain of salt. There can be better hardware, there can be more efficient error correction. algorithmic improvements, analog simulation. It doesn't mean that we cannot do meaningful things, but I think it should be guiding our efforts, what we should do. And I think speed is important and quality is important. And for me, also with limited resources, I don't focus on quantity in any of my research topics. I try to focus on the first two, and I think with superconducting qubits, we're good. And I will give you a short glimpse of what we're trying to do to get potentially better quality than what we have with current standard qubits. So how can we avoid errors in the superconducting qubits? And again, very big picture view first. You can filter all the noises, so shield your system better from the environment. And you can do active error correction. And probably you will need all of those. But you can also try to do something called has been called error protection. That is, you try to design a circuit which doesn't hear the noise. And one big picture view you can have is topological protection. And we don't do that, but one way to imagine what that is you can, I stole this from John Preskill. Think of a quantum book where all the contents of the book is encoded in the correlations between the pages, and the environment has only access to one page at once and cannot access the quantum information. And that gives you, through the global encoding, you get protection. And you have to have a certain way of reading the book, all of the pages together, so you can extract the correlations to actually operate on this. And this is an analogy, imperfect, but maybe it gives a sense of what we try to do here. This is an example that is more prone, more adaptable to superconducting qubits. What we actually do is we try to engineer the wave functions of these circuits for example, here in the space of charge in the charge variable. And you see this is a discretized wave function, for example. And if we spread out the wave function as much as possible over this parameter that might be noisy, we get very insensitive to these noises. And that helps us not to hear, basically. And if you look at the wave function of the excited state, you see that it's also spread out, but it has actually zero overlap with the ground state. And that means the matrix elements are zero, and therefore bit flips are not allowed or very improbable. And so this is one way you can try. This is the sort of a grid state encoding to protect these circuits better. Now we do this with circuit elements. In classical integrated circuits, you have these circuit elements. In the quantum domain, we don't like resistors and resistive elements. And the world would be a little bit too boring if you only had capacitors and inductors and harmonic systems. So thankfully, we have these thing called Josephson junctions, which is a nonlinear dissipation-less, more or less, very largely dissipation-less circuit element that makes our circuits anharmonic. It gives you a sinusoidal potential. Okay, so, and it also imposes the typical energy scales we can achieve with these circuits then, and the fact that we want to be in a ground state determine that we need to work at low temperatures. So the circuit we like to play with these days is an RF squid. It's an inductor and a capacitor shunted by a Josephson junction. It's a very simple system. There's very rich physics. And the best way to visualize the physics is you have the Hamiltonian with the kinetic term, and that's the charging energy, the energy you need to charge the island or the top with an extra Cooper pair. And it's equivalent to the mass of a phase particle moving in a potential that's given by the green part. And this potential and the wave functions are drawn here. And as a function of the flux through this loop, you see that you can have a well-defined ground state in the center to more or less degenerate states here. And we have a lot of, this is not as rich as atomic physics yet, but in contrast to atomic physics, I would say we have a lot of freedom to engineer all of these aspects. So for example, if you vary the Josephson term, what you do essentially is you change the size of that sinusoidal potential. If you change the inductive energy, you change the parabolic confinement. And if you change the capacitance, you change the mass, so the density. And with that, we can, for example, build systems that behave like transmons, like in this case, even though it's an RF squid. And probably time doesn't allow to look at all the things, but basically we built this inductively shunted transmon qubit, which is like a huge transmon with a huge inductor shunting it. And we went to a regime where in this double well potential, the matrix elements 10 to the minus 13. And to cut the story a bit shorter, we showed a few nice things with this, like such as measurement of quantum jumps without using a JPA. But maybe more importantly, we showed that because of these small matrix elements, we can have our particle be stuck up there, and the typical lifetimes reach like 3.5 hours for bit flip times. Now, what is missing here is coherent control because the wave functions are so disjoint, and that is what we are currently working on in our lab mostly. And we just put out a proposal for implementing single and 2 qubit gates using DC pulses, where you basically tune within a few nanoseconds the tunneling barrier to implement single and 2 qubit gates with fairly high fidelity. And if you want to know more about this aspects, please let me know after the talk. And then, so with that, this was a glimpse into the first area we like to work on, which is coherence and exploring new circuit elements, also smaller circuits. The second area is interactions, also with mechanical systems. And the third one is networks. And here it's really about trying to find a way to connect different cryogenic systems via room temperature links. And why that is interesting, I'll tell you now. So this is the outline, the main part of the talk. Why are microwave optical interconnects interesting? And I want to give you a sense of where the field is. I want to tell you what works in our lab. We did a number of interesting experiments. It also allows us to probe the resilience of qubits with regards to light fields, in our case, at telecom wavelengths, and some of the challenges in ongoing work, including working with single photons. And I doubt there's enough time, but if there is, I want to also highlight a recent experiment that started to work where we have a collaboration with Peter Rabel. All right, so this work has been done at the Institute of Science and Technology. It's about 15 years old, 20 kilometers from Vienna. We have now 90 research groups. In this building are our labs and clean rooms. And it has not just physics, it's also computer science, math, life sciences, and chemistry now. The work I'll tell you about has been initiated and started with Harald Schwefel, who was at the Max Planck Institute for Science of Light at the time, and now in Otago. And the entanglement work has been done by Rishabh and Liu. These guys helped us with the theory, and the readout, qubit readout work has been done by Georg and Thomas, and this is the new team. Okay, so why are they interesting, and what are the relevant figures of merit? So the first aspect that makes it interesting is also recognized by some of the big players like IBM and so on, that it could serve as the outermost layer that connects different fridges. So it helps with the modularization of a very complex system. And it might help to build like LANs and stuff like this. Yeah? Telecom links are great. They're low loss and noise resilient. A room temperature link at the microwave frequency of 10 gigahertz, you have 600 phonons, so 600 thermal photons present. That will immediately kill your quantum information. The second thing I find very exciting is the possibility of building hybrid networks. I don't have a plan to why that makes a beautiful product, but so I don't know what it's useful for. But I think it would be really cool if you do some qubit photon entanglement, which already exists with ion traps, for example, in Innsbruck, and do your Bell measurement and actually entangle the common mode of a superconducting circuit with an intrinsic state of a single ion, for example. I think this would be really cool. The other motivation is you can use wavelength division, multiplexing, and similar techniques, plus the very low thermal conductivity and compact size of optical fibers to control, to multiplex the control for qubit systems. And I heard that here at the WMI, there are also projects in this direction. The other thing is that also on the output side, and I will show you that. Output is later. So then also on the synthesis side, it can be also interesting. So some of the superconducting circuit work is now capable of building very exotic states that are hard to get in the optical domain. So you could try to convert them, including cluster states. And for the sensing and readout part, we have in our system a very nice analogy with optomechanics, where basically instead of the mechanical motion that you detect, for example, with systems like LIGO, you could build similar systems and similar techniques to detect RF frequency light. And I will show you that we can read out a superconducting qubit only with optical signals and local modulation and demodulation inside the fridge. Once you have a distributed system, you can try to apply it for some of the ideas that have been developed for distributed system and scalings where you share entanglement. Okay, so what do we need for the different applications? There are a number of figures of merit out there, and everyone picks the ones, of course, that let his system or her system look very good, and we did the same. but basically my approach was coming from the superconducting qubit community, not from an optical quantum computing or communication community. I did not think about heralding in the first initially, but about deterministic protocols. And so the way I like to think about it is similar to an amplifier. And if I use a phase insensitive linear amplifier model as put forward by Caves, you can calculate basically the input noise is or what I call added noise here is some technical noise. It's what you typically have in your spec sheet. It's the added noise of your amplifier due to electronics, for example. And you have a transduction coefficient for an amplifier would be typically larger than 1. But you also have, if you look closely, if you don't work in this limit for large gain, you also have that quantum noise term. Basically, you mix in the vacuum as you lose your photons. And what I try to do here is in the z-axis, and these contour lines are the sum of those two contributions, that vacuum noise plus the added noise. And as a reference point, I put here an experiment from EPFL, which used a commercial phase modulator, which I put at 4 Kelvin. And you see that it has fairly low efficiency. And here, I mean, efficiency is like an S parameter measurement, which counts in terms of photon number. It's not, of course, there might be a large power gain, for example, because you go from, for example, 10 gigahertz to 200 terahertz. But what I mean here in this transduction coefficient is in units of photon number. Okay, so basically a JPA or a HAMT would be somewhere up here. So you can also compare to those if you want to do a readout task. And the field has progressed quite a bit to basically approach this point. You want to, for a fully deterministic interface, you don't want gain, you don't want loss, and you don't want any technical noise. In which case, and that is actually amazing, you could have a quantum state at 10 gigahertz and convert it without adding any extra noise. In theory, it's possible with these parametric processes. And so these are some of the results over the years. And you see that the early work from Conrad focused on high efficiency, but has still suffering a bit from a bit too much technical noise. And a lot of the other experiments basically started down here below this line. And it turns out this is an important line because, of course, in quantum communication, you're dealing with a huge amount of loss in general. So there has been a lot of protocols developed that use other resources like shared entanglement, for example, to transfer information. And you can use those tricks, for example, to do quantum stuff down here. You don't have to be here. And that's good news because so far nobody got there yet. So we started up here, and with our pulse sources, we got down there. All right. So that's what I just said. So if you're down here, we can, for example, distribute entanglement and teleport the state. And in addition, herald on successful events with SNSPDs. So that gives rise to a different figure of merit, and that is how many times per unit time, how often, what's the repetition rate or the success rate. And on that plot, we're not doing quite as well. So on that plot, the more integrated devices are doing better when you have bandwidth times the duty cycle. And of course, you want a high enough instantaneous bandwidth to actually match what comes out of your superconducting chip, for example. And we work with around 10 megahertz, which is perfect. And for the superconducting qubit side, for an ion, it would be plenty. You might have even want a lower bandwidth. But if you want to connect to a semiconductor single photon source, it's too slow already. So we are somewhere in between with that. All right. And then there are technical things that give rise to different values for the more procedural side. So the most developed systems that were on the previous slides are these membranes. We also have a fully integrated silicon photonic version of this, mechanically mediated transducers, very high power efficiency. In fact, we needed about 1 billion. Yeah, we needed about 1 billion times lower pump hours to mediate the interaction parametrically. But still, we had too much mechanical phonons that would produce too many noise photons to do quantum experiments. Piezo optomechanics is very promising right now, with a lot of interesting experiments done there. And in Rydberg samples, people have also achieved this transduction below the dashed line, basically. And I will tell you today about our electro-optic transducers, where we were able to realize all those things that I mentioned in the other cases recently. All right, so what do superconducting and optical? Well, what I want to answer here is what we can do, and this should give you an answer if superconducting and optical photons get along, and if we can upconvert non-classical states so far. I will start by explaining how our device works. And it's a bit old-fashioned, to be honest. It's a bulk crystal lithium niobate whispering gallery mode resonator made from one of these wafers. We make them in-house. And we use the Pockels effect, which is basically the effect that if you apply voltage, you change the index of refraction due to the Chi2 nonlinearity. And this is because of the non-centrosymmetric crystal structure. Now we embed this material at the same time in an optical resonator and a microwave resonator. So basically the index of refraction modulates both an optical and a microwave resonance. And this allows us to get spatial mode matching, phase matching. If you pick the correct tensor and polarization, it can be power efficient. We make it resonant, triply resonant, and we can select the desired process because this parametric interaction can give us both either amplification or cooling, either state conversion or two-mode squeezing. And the interesting thing is if you manage to restrict this to just two optical modes, there's a more almost exact mapping to the physics of cavity optomechanics, where the displacement is mapped to the voltage and the momentum to the current in the circuit. The cooperativity of the process is, I would say, it's the probability that you actually convert an existing microwave photon to an optical one. That is that the voltage fluctuations of that single photon, which is on the microvolt level, are sufficient to produce a sideband photon in the optical domain, how close to 1 that is. And that is a function of the dissipation rates of the two resonators, the coupling on the single photon level, and the number of pump photons. This is a rendering, how it looks. So it's basically a disk around 100 micron thick that is polished. And that disk houses with spin gallery modes. This is a cartoon because in the optical domain at 1550 nanometer, we have about 20,000 nodes. And for the microwave mode, we have 1 node. And that forms sort of like a gearbox where you have phase matching and energy conservation. So basically, you apply a pump, and if a photon is present in the resonator, in a microwave resonator, you will produce a blue sideband, which cools the resonator, and vice versa. If you manage to suppress the two-mode squeezing interaction, if you pump on the blue side, you get so if you suppress this side, you can also get pairs of photons in a direct analogy to spontaneous parametric down conversion, now 1 at 10 gigahertz, 1 at 200 terahertz. And we select the desired process by picking a mode where we hybridize with an out of polarization mode, and we can pick then which side we pump to shut off one of the two processes. Okay, so we got to fairly high cooperativity by pulsing the pump with close to 1 watt. And that gives us around a nice bandwidth, so we can do 100 nanosecond pulses. And we get about 99% or more internal conversion efficiency. That means if a microwave photon is there, it will be for sure converted to the optical side and vice versa. But in practice, we have around 15% bidirectional conversion efficiency because we need to couple these photons out and we need to couple them photons in, and those are all coupling losses in the end. All right. You can also IQ modulate the input and observe the result on the output. And we can try to push to even higher. This is a cooperativity of 0.5 roughly to close to 0.9. But we ran into a parametric instability. And so that didn't allow us to observe the strong coupling limit yet, where microwave photons and optical photons won't interact strongly in a nonlinear crystal. We did, however, observe effects like dynamical backaction in direct analogy to optomechanics and atomic physics, where you see electromagnetically induced transparency. But I don't have time to show that today. The important thing is that we achieved this also with low noise. That is the challenge. All right. And because we got high cooperativity and low noise at the same time, we could do this experiment where we try to entangle microwaves and optical fields for the first time. So what you see here is that we basically now turn on the two-mode squeezing interaction. We pump the blue detuned mode and observe the light coming out at the red detuned mode and the microwave cavity. And you do this 1,000,000 times. And here you see we have a detection noise floor. That's an imprecision noise due to the amplifiers we have and the losses we have in the detection channel. And on top of that, you see signals coming out. If you do FFT analysis, what happens before, during, and after the pulse, you can back out these spectra. And this is the power spectral density. And we can back out with a tiny bit of theory the thermal occupancies of the modes, which is less than, it's just a few percent. Actually, it's on the order of 7% after the pulse, 9% after the pulse. So during the pulse, we heat up a little bit. But the two-mode squeezing signal is around half a photon on average. Now, on the optical side, we only get thermal light when the two systems are coupled, so during the pulse, not before and after. It's pretty cold otherwise. It's at 10 millikelvin. And basically then we extract the quadratures during these time intervals instead of just the power spectrum and calculate the correlators, the covariance matrix. And what you see here is basically the photon numbers on the top. The yellow are the correlations that we observe in the covariance matrix. And from those, you can calculate the two-mode squeezing between the microwave and the optical field. And you see that we are nicely squeezed below 1, which according to Duan and Simon are proofs that we have a non-separable state that is entangled. Generally, the theory fits fairly well, except for a little bit of coherence that we seem to miss, likely due to phase fluctuations in the laser. Okay, so some of you might ask, what is it good for? If I have enough time or after the talk, I can show you an experiment by one of my students who uses two-mode squeezing to entangle qubits in a remote way. But with this result, this was not possible. It's too hard. First of all, we don't have a qubit in the optical domain. And secondly, this is a pulsed experiment with very low rep rate. And if you do a calculation about what it means, we entangle about 0.1, we generate about 0.1 entangled bits per 200 nanosecond pulse, which unfortunately we can only repeat twice per second to stay cold. So there's no real protocol we can implement here with this for now. But it was exciting to us because microwaves and optics were produced together and showed the strong correlations. What was entangled really were the output modes right after the cavities. The losses to room temperature, for example, already destroyed this entanglement. So that is another challenge when you work with two-mode squeezed protocols or with continuous variable protocols that are very sensitive to loss. All right, so the next step for us was to involve a qubit. And I already gave you one motivation of this whole business is to, or could be, to use the things that have been developed for optical communication in data centers to harness the higher bandwidth that we have in fibers, to harness the low thermal conductivity to actually control superconducting circuits. And of course, you should be worried because 200 terahertz is much higher than the gap of the superconductors of about 100 gigahertz that we use. These are a huge amount of energies, and people these days are worried about cosmic rays and all kinds of things, right? So basically, there was a big question: is it the worst idea possible to put optics in a fridge with a qubit? And that is part of the answer I want to give you today. But the vision would be to replace this with a fiber, yeah? So I'll show you what we got done. So what has been done before? The input or control side very recently by the Harvard group has been done with also electro-optics, on-chip electro-optics. And of course, I already pointed out the work from the NIST group using photodetectors to produce microwaves at millikelvin temperatures using an optical fiber. The photodiode approach is very wide band, which is beautiful for controlling many qubits. The problem is it's inherently absorptive, while all the other processes we try are parametric, which means in theory they could be lossless, but of course in practice you always have some heating and some losses. So far, but I guess it's a matter of how hard you try. On the RF output side, there has also been a few experiments previously, and also people have transferred directly excitations qubit excitations that were hybridized with a mechanical system via optomechanics in my previous group at Caltech. So now what we do is we combine both of these sides. We do both at the same time. And we use a standard qubit in a standard 3D cavity, and we use a fairly standard dispersive readout, where basically if the qubit state changes, the frequency of the microwave cavity changes, and we basically detect the shift in that frequency. More precisely, we use, because our transducer actually degraded over time, we didn't have any more of those nice efficiencies. That's why we had to so that limits the sensitivity. We couldn't sense individual photons anymore, so we use a high power readout here, which is based on a lot of microwave photons, which we read out optically. We did this readout basically in this one cool down with one qubit, and with different configurations. And this is sort of the standard configuration with microwaves. This is a hybrid where, similar to previous people have done, using a microwave probe tone and then converting the result to the optics and reading that out without using an amplifier. And here, this was kind of the new way. We only use fibers, and we demodulate the microwave here and then modulate it at the same time again to the optics. Again, the main difference to a commercial modulator is really the sensitivity. So again, it's not single photons, but it's fairly low photon numbers, and it's not like volts level modulation here. All right, and the way we implement this in a single cooldown is basically by changing the state of that circulator there, and actually those two, yeah, okay. And those two experiments we actually do at the same time. We use part of the signal to amplify it in the usual way, and part of the signal we actually convert to optics. All right, but I will only focus on the left and the right, which is the most different ones. So basically, we use a classic way to drive the qubit here on the left to prepare a ground or excited state. Then we send a microwave pulse. We detect what is reflected, and that's about it. And if you do this, record a time trace of this, you see you get a very different response depending on if you're in the ground state or in the excited state of your qubit. It's done at a very particular power, at a very particular power and frequency, where basically there's no resonator there unless the qubit is excited. Now for the optical side, we have an optical pump, and we have an optical signal that is basically modulating that pump, and that generates via down conversion a microwave tone that is reflected back, and depending on the qubit state, that reflection is modified. There, we shut off the circulator by opening that switch, basically, which makes it ineffective. And that's how we do both experiments in the same cooldown. And basically, we see then a small change in the optical response depending on the qubit state. And here you see we are on a big background here. We also have to take into account some dynamical back action effect because we go to fairly high cooperativity, and the relative signal to background is not much lower than before, but because the optical readout is pretty good without any amplifiers and such, we get a nice signal to noise ratio and a nice nice distinguishability. And you can also see this in the single shot traces. These are the single shot histograms with about a readout fidelity of about 90%. This is certainly not state of the art on the microwave side, but this is also because we capture only a small part of the light for this measurement comparably. And the reduction is fully described to about 82%, is fully described just by this offset because we don't even have a circulator. And there is for the optical readout. So we have the full pump that we measure and just a small change of that pump depending on the qubit state. So we have single shot readout without using coax, except for this part. And what I want to highlight is that this is also a measurement of the qubit without using a circulator. And usually, you will, as a student in the lab, I guess, typically, at least was the case for me, you cannot do a quantum electrodynamics experiment in the microwave domain without circulators. You need them at least for two things. One is you need to shield the output line. So basically to avoid that you have 4 Kelvin noise propagating towards your system, and you cannot just attenuate it like on the input line because you need to read out. And you want to isolate the reflections. If you did a reflection measurement here with a single line and no circulators to distinguish the input from the output, it would be horrible. Like you would have reflections everywhere, and you wouldn't see the last one for sure. And so it's kind of nice that in this case you produce the microwaves at the millikelvin temperature, so you don't need the attenuators. You read it out at the millikelvin temperature without amplification or thermal radiation coming back, so you don't need the isolation either. And circulators are bulky and expensive, so I think it's a nice aspect of this work. All right, so one question remains: does the qubit care that it's read out with optics or not? And one of the most straightforward ways to answer that is, or to give you the answer up front is, we did not observe any radiative impact, but we observed thermal impact, which depends on how much power you dissipate there in general and only via the fridge. Now, of course, if you had a better qubit, I'm sure you might be more sensitive to see something. Here we definitely had some problem with shot noise dephasing and such. But for the qubit we had, if you read it out with the three different ways, we saw pretty much the same T1. And actually we saw, if you look closely, the red curve, a slightly better T2 than for the others. And this is because we actually turned off the connection to the output line, which I think was also contributing to thermal shot noise dephasing. So this is one thing you can do. We went a bit more in detail. So for example, here you see, and to do that, we wanted a more sensitive way to do these measurements. And so basically, we now use a chosen parametric amplifier to do the readout. It's not a high power readout anymore. So it gives us a nice Q&D readout. Still, the capturing efficiency is not very good, which is why we're not closer to 100% readout efficiency. And we do the readout twice, and we do it in the presence of light or not. So it's not an optical readout, but it's a microwave readout, a very sensitive one, where we use the same optical pulse that we use for the optical readout, and to see its impact. And what you learn from a measurement like this, for example, is that the first time you read out, you have some 95 something percent readout efficiency, and then the second time, some 92. And you can explain why that is. In this case, it's because of the finite bit flip time. And from that, you can calculate a quantum, a Q&D parameter, like how quantum non-emulation is this measurement. And that's the orange curve. And what I show you here, I will explain you where the theory is coming from. But what I show you here is that it's pretty good. It's pretty close. Q&D-ness is high when the laser is off. And when we turn it on, it's also good. But as we increase the repetition rate of the experiment, everything degrades. And I will tell you why. The same for the T1 and T2 times. When the laser is off, or if it's on, same instantaneous power, no difference. And then as we increase the rep rate, things start to degrade. So in order to explain this, our hypothesis was that basically there's no direct impact, but the optics heats up the fridge. That depends on the integrated power because of optical absorption. When the fridge is warm, a lot of bad stuff happens. And so we did thermometry, and the yellow line is basically just the ruthenium oxide sensor in the fridge. Again, as a function of repetition rate, you see we go from below 10 millikelvin to above 100 millikelvin. We did noise power measurements of the EO cavity output. This is a direct thermometry, a noise thermometry method, which gives us the brown line. And there you see where all the heat is coming from. It's basically the disk is absorbing a small part of the optical light, and that is heating up the fridge. We also measured and actually these scalings agree with what you would expect from a blue force or from a dilution refrigerator system, because the thermal, the cooling power scales also with the temperature. And basically we also measured the qubit and the qubit cavity temperature via thermal induced Ramsey oscillations and thermally populated Rabi oscillations. And you see that the qubit and cavity are okay. They're way too hot from the start, even when the laser is off. That's our bad. But when the laser is on, it doesn't really change much, unless at some point the fridge temperature approaches, and then that's when we have the bad impact. So basically, we can roughly understand the scaling laws of these temperatures. They're not surprising, and we can use them to basically fit the readout in this case, and also the decoherence times, where we introduce blackbody radiation, thermal quasiparticles, Purcell effect, and that's where these theory lines come from. And we get pretty good agreement with theory, and the effect is indirect thermal heating. So to solve this, we just need to build a system that is more power efficient and or that absorbs less of the optical light. So I would say it's good news for this field or the approach that we don't see a direct impact due to light at telecom wavelengths. Seems to be different for high energy particles. There was no specific shielding between our transducer and the qubit system. There was just a coax, and still this was the case. Is it useful? The answer is probably no. At this point, not. One thing I find exciting is that this is a way to do RF sensing without electronics, and it also would work the same way at terahertz frequency where you don't have electronics. So I think it's a potentially nice way to build sensing elements. Also much more sensitive, hopefully soon. We need to reduce the active heat load, and I mentioned before, in on-chip devices, we used as low as 1 billion times lower power. So I think that is a clear message that those mechanical devices could be perfectly suitable if you get the correct bandwidth to do this much better. But also there are challenges to get away the heat from the chip. All right. So what are we doing right now? This is work in progress, and I'll try to make it short. So next step for us is to entangle a qubit with an optical photon at room temperature. And I already told you everything we did so far is deterministic. It's not what people do in communication systems and quantum communication systems. So how do we get there? We generate a Fock state with our qubits, emit it, and entangle it with our qubit. We chose time-bit entanglement encoding. So we developed a protocol to generate a state of the qubit being in the ground state with an early photon leaving the system, and the qubit plus or minus the qubit being in the excited state and then a late photon leaving. There's some preliminary results that this starts to work, and we identified immediately a challenge with our current system. Only about 1/10 of those photons is actually arriving inside the receiving cavity. So we have to work hard to make catch and release and set up improvements basically to bring this efficiency up. Because if you only have 1/10 occupancy that you care about, the thermal occupancy needs to be even like 1 part in 100 or so, and that is going to be really hard to be cold enough. And you see part of that later in the later slide. Good. So also, given the limited fidelity, we need very low added noise. That's the first challenge. The second challenge is after the transduction, we need to detect these photons and at room temperature. And because our system is not very power efficient, our pump is around 10 to the 14 times stronger than that single photon, which means we have to filter a pump by about 140 dB without killing that photon at 9 gigahertz away. So we built a lot of filter cavities, and we are doing more and more free space optics because it turns out there's a lot of Raman scattering in fibers, which I didn't know about very much before we started this. So yeah, these are home-built filter cavities. We want the bandwidth, which is why we don't work with one, but with cascaded systems, we also have to clean the laser very well. And here are first experiments where you show that we can convert a traveling Fock state that is emitted by a superconducting qubit with a reasonable signal-to-noise ratio. And we can also do Rabi oscillations of the qubit, and then we observe the Rabi oscillations in the optical photo detection. We can also do the microwave analysis of these Fock states and get the Wigner functions of those microwave states. Now, the last slide is what are the obvious further improvements? We need, sure, we can think about on-chip devices, but basically the main things are the initial version of this was not very practical You could close it once, the second time the disk would break. So basically, we went to a thin film evaporated electrode with a central clamping. As you see here in the middle, these clamps changed. This is now much more reliable. This came at the expense of lower G. So we have now started to develop an industrial process to shape these disks to a wedge and then do evaporation like that to also get high G. And then next step is to work on better coupling with maybe with photonic crystal couplers, on-chip couplers, to get rid of this free space coupling, which is a real challenge at low temperature. I think with that, I will end. And this is my summary. Thanks for your attention.
Thank you, Johannes, for bringing us in touch with the combination of optics and superconducting circuits. The floor is open for questions. Please shoot. I have a question for you. I'm actually surprised that you suffer really from fridge heating, as I understood you, because I would have naively assumed that if you pump this amount of energy, optical energy, into your, I don't know, crystal, and you have absorption, that you should suffer first and immediately from thermal excitations at your 510 gigahertz, and that this travels down your microwave line and spoils your qubit, and not that you're heating up the fridge.
Yes.
Can you give a little bit more details? Because
yes, you're right actually. So this is this would be the foremost and the biggest problem. I mean, what is it? So the EO cavity is at 1 Kelvin already. The good thing is, when you do this high power readout, you actually detune the EO cavity frequency from the qubit cavity frequency on purpose, because when the qubit is excited, you find the resonance frequency 2 chi, or it's a different chi, but whatever, a few 10 megahertz away. So basically, only when we do, in the moment when we do the readout, the frequencies are aligned, and in all other times, it's actually rejecting that noise because of frequency filtering.
I see. More questions? Yeah.
Me?
Thank you. Yeah, so I was wondering, like, what the main source of the heating from your optical link is. Is it like, I mean, you mentioned it's absorption in the EO cavity itself, or is it also due to the finite coupling you have from the free space link to the EO cavity?
So when we I don't have data to show this, but you're mentioning, is it scattered light, or is it actually the intracavity population?
Exactly. Like, so if you go to like I don't know, if you improve the coupling into your chip device, so can you gain?
I think it's dominated by the intracavity light. There's a huge intensity in that cavity. It's our optical cavities has a okay, finesse is what matters, but this has a Q of about 10 to the 7 to 10 to the 8, depending on which experiment we're doing. So actually, there's a lot of light circulating there. We apply up to a watt of power. So we did sweeps, basically checking temperature as a function of detuning of that pump, right? And it was, if I remember correctly, it was more proportional to how much light is in the cavity, not how much light we send into the fridge. We tried to design the system also such that reflected light would go back out. That is not hard to do in this kind of free space setup, but part of it should.
Thanks for the very nice talk. I maybe have a small question on this one, whether you understand why the qubit is actually much hotter than the base temperature of the fridge. And then the more general question, kind of, what is your feeling going towards integrated devices, 3D integrated devices, all on-chip fabrication, and then scaling also transducers up, which is kind of not the direction that you seem to go. It comes with extra troubles and challenges. So maybe if you can say a few words.
Okay, first question. all I can say is that in this fridge we reproduced it, and obviously something is broken. In some of our filters are not working the way they should. Also, when we don't have the laser turn on ever once, still, it's a setup problem, and I cannot tell you what it was or annotators.
Fine. Sometimes know why things are.
Promise next time I will not use the same excuse. We have to fix it. The second question was integrated devices. So I don't think it's a good idea to have the qubits on the same chip as the transducer. This modularity, like for example, the work from Austria I mentioned, couldn't do this entanglement experiments because every time they did a transduction event, the qubit died for a while. It's really going normal conducting. So you cannot have a qubit photon entangled state that way. So sure, you can separate things on the chip as well and might work. But if there is not a real reason to do it, I would try to avoid it. Then integrating the transducer, I think it's a great idea. Others are doing it, so I try to find my niche, not doing it maybe. We are basically, why our experiments work is because we use a trick here in the end. Our system is so large and has such a high heat capacity, and it has a high heat capacity and a lot of surface volume to thermalize. So basically, because we do these pulsed measurements, we have a bandwidth of 10 megahertz, but our heating rate is like about around 1 thermal photon per second almost. So we heat up much slower than we convert, and that allows us to do stuff in the ground state as long as we don't repeat it too many times. Now, the major issue here is that our thermalization rate is still way too low, and the powers we need are way too high. And we are addressing this with some of these things. Basically, for us, the next step. So basically, I want to integrate everything, but the crystal. I want to keep the big crystal, but we are, for example, experimenting with normal conductors here now, and we're experimenting with new shapes, and we want to integrate it maybe in a flip chip device, and we want to integrate it with optical couplers and all these things. But because we have seen that in previous work, if you use a photonic crystal cavity, which can localize your field by 1 lambda cubed, and you get huge couplings. Still, the smallest amount of heat will, like that optical power, those few photons you absorb generate a lot of noise, and you need to get rid of it. And that's easier here than on the chip. So for now, I want to keep it modular.
Yeah. Maybe a very simple question, which you might have addressed during the talk, but I didn't get it. I apologize in advance. So if you talk about the superconducting optical entanglement or these networks that you have in mind and the conversion, what is roughly the efficiency of this process that you can experimentally achieve?
So for converting a coherent state, we got really about 15% efficiency between the signal that is applied at the input port and the output port of the device. Now, for the entanglement,
the coherent state has how many photons in this example?
The efficiency doesn't depend on that, I would say, but it was easier to measure a large coherent state, so this was large.
Yeah, how large? 1,000, million?
I don't remember even.
Yeah, roughly.
Probably, definitely thousands, maybe million.
Okay.
But so now the last thing I showed you was a single photon, though.
Yeah.
And actually the efficiency there was not very good, but it's not because it's a small Fock state, but because the device got bad. And the efficiency or cooperativity scaled with the applied pump power. So I could always, in theory, get unity conversion efficiency, but then, of course, if I heat too much, then the single photon doesn't.
Exactly. That's why I was asking what you can achieve in practice.
That was the whole point of this map that I showed, where you have added noise and efficiency, and you want to have low added noise and high efficiency. And basically in that paper, we showed that we can have around 15% total efficiency with added noise of less than 1. So add noise photons. And that enabled these quantum experiments.
15% from superconducting to optical.
The internal efficiency from mode to mode is 99, higher than 99. It's a coupling losses of about, I don't know, 50% on each side or so. Okay. Then you have 0.5 squared or something. So for the entanglement now, we want to use heralding, and I actually didn't explain this. So the losses wouldn't, so this efficiency wouldn't be so bad, right? A lot of quantum experiments are done with lower efficiency than 15%. So
don't misunderstand me. I'm not saying that 50% is not good.
Yeah. No, the efficiency was really high in this device. It's maybe one of the highest, if not the highest, and the noise. The rep rate is low. Once you do these heralding tricks, you want to repeat this really a lot of times, and there we're not exceeding the others at the moment. So we have to work on faster thermalization. That's one of the technical things we want to work on. Not sure if I answered the question, but I tried.
Yeah, so my question would be, do you think it's feasible to extend quantum networks, networks based on superconducting processors via entanglement swapping and entanglement purification? Do you think that's something feasible in the near future?
Mm-hmm. Small scale demonstrations, with small I mean few nodes, I think it's definitely feasible, and we want to do this. That would be the next step, to have 2 qubits and then do Bell measurements, right, of these qubit photon entangled states. But this I mean, there needs to be huge improvements in power efficiency in these devices to actually use this, and also fidelity. Well, more in rep rates. Once you do heralding, really, sure, I do believe you don't want to do your very expensive quantum computing experiment, and you have calculated halfway through, and now you want to swap with the other guy, and you have to throw it away 99% of the time because the transducer didn't work. I don't think that's gonna fly. But people are, I don't know, things will improve, and I don't know, as a high level link, maybe. I think you're better off scaling the size of the fridge for now and making better qubits, so you don't need so many qubits for now.
Yeah, and also the efficiency of swapping and purification goes down quite significantly with the gate infidelities, and that's also the infidelity is already pretty good, but compared to other platforms, superconducting qubits still have relatively higher infidelities, right?
Yeah.
Yeah, and that was my question. Thank you.
I think at the moment, the main issue of this, even if you get quality high enough, is just the channel capacity. It's like really low. It was actually quite low for all quantum networks, but here it's even lower. But this has to be, I don't know how much it is just technical or fundamental. I think so far it's technical.
All right, thank you.
Okay, I see no further urgent questions. Do we have questions on the Zoom link? And let's thank Johannes again. Thanks for coming. Material.